Okay, good morning, afternoon, or evening, everybody. Welcome to the NASA PO.DAAC State of the Ocean webinar. This is your host, Jennifer Brennan. While everybody's logging in, most of you have already noticed this, but we do have two optional polls located at the bottom left and middle portion of your page, and we very much appreciate your feedback on these polls. I've got 2 p.m. Eastern Standard Time, so we're going to go ahead and get started. First, what I'd like to do is just quickly review a few logistics related to this webinar. To ensure the best audio experience, the conference has been placed in silent mode. However, if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod. This works like a chat, and you'll find that located on the lower right-hand corner of your screen. Today's webinar is being recorded. The recording will be posted to our online Adobe Connect webinar catalog, as well as to our NASA Earth Data YouTube channel within a couple of days of completion. And what I'll do is I'll send an email to all of the registrants with links to both recordings. In addition, today's presentation files are available for download at the end of the webinar. As far as timing is concerned, today's webinar is 1 hour long. We've allocated 45 minutes to the presentation and demonstrations, with an additional 15 minutes for the question and answer period. Once our speakers have finished their presentations, what we'll do then is we'll move to a final set of optional polling questions, and then from there we'll move directly to the Q&A period. And just one final note, depending upon the volume of questions that we receive at the end, we'll extend the Q&A period an additional 15 minutes to 3:15 p.m. for those of you who may wish to stay on the line. And now let's pull up today's agenda. Let me pull that up for everybody here. Okay, during today's webinar, we have 4 speakers. Our first speaker is Eric Tower, who is a project systems engineer at NASA's Physical Oceanography Distributed Active Archive Center, or PO.DAAC. He will kick off today's webinar with an introduction to PO.DAAC. And then from there, we'll transition to our second speaker, Kathy Toe, also a systems engineer at PO.DAAC. She'll provide some context for all of you with an overview of the State of the Ocean toolkit. And then next, our third speaker, Flynn Platt, a science applications and data interaction engineer, will take you on a tour of the SOTO application, and he'll showcase the tool's key features and functionalities. Finally, we'll wrap up today's webinar with our last speaker, Ed Armstrong, who is a data engineer at PO.DAAC. And what he will do is highlight some of the science applications for this tool, to include a use case, and also show you how to download the underlying data using Panoply and the Threads data server. With that, it is my pleasure to introduce our first speaker today, Eric Tower. Eric?
Thank you, Jennifer. And hello, everyone. I am Eric Tower, and I am the project system engineer, as Jennifer mentioned, and we're going to go ahead and get started, beginning with an overview of PO.DAAC, which I'll provide to you to just give you a sense of context. And then Kathy will go ahead and give you a first look at SOTO and its key aspects, followed by an in-depth walkthrough by Flynn. And finally, Ed will show you some of the exciting science that you yourself can view within SOTO, some of the science that we at PO.DAAC are directly here to facilitate. So let's go ahead and begin with a quick view of PO.DAAC in the ESDIS context. A NASA DAAC is a Distributed Active Archive Center, and what that breaks down to is 3 major pieces. There's distributed, there's active, and there's archive. So the NASA PO.DAAC, which stands for Physical Oceanography Distributed Active Archive Center, is one of a dozen DAACs within NASA's Earth Observing System Data and Information System, or EOSDIS. And a DAAC's job is to manage, archive, and distribute Earth science data as part of NASA's Earth Science Data Systems program. EOSDIS then provides end-to-end capabilities for managing NASA's Earth science data. Now, these data represent some of the most complex and diverse Earth science data sets on the planet, and they come from all sorts of sources, including satellites, aircraft, in-situ field measurements and instruments, and numerous other activities within the NASA Earth Science Division. As you can see, there are a dozen DAACs, 12 of them, and they are distributed, so there's that first word, distributed across the country. And each one is very intentionally located within a center of excellence for those disciplines that it supports. So you can see that the PO.DAAC, the Physical Oceanography DAC, is right down there in the bottom left in Southern California at NASA's Jet Propulsion Laboratory. So our charter here at PO.DAAC is to ensure that NASA's physical oceanographic data is properly cared for, managed, and preserved for future generations. And as our primary responsibility, we are always looking for ways to perform that role more and more efficiently and effectively. So that's the archive part of our name. But while managing hundreds of terabytes and soon to be petabytes of unique science data can be a challenge, we are not simply a data center. In fact, a key aspect of our role, and directly included in our charter, is to ensure that the data is also easily accessible, usable, and understandable. That's the active part of our name. And through our various tools and protocols and information services, we work very actively on making sure customers of all contexts can be guided toward the proper data for their application and understand the data and the science that they are uncovering. Here at PO.DAAC, we have 7 earth science parameters tied to physical oceanography that we manage, which includes things like ocean surface temperature, sea surface height or topography, salinity, winds, gravity, currents, and in the same spirit of ensuring that that data can be used and understood, we also serve some other data sets from some of our sister DACs, such as ocean color from the Ocean Biology DAC or sea ice from the National Snow and Ice Data Center. And PO.DAAC in general has 3 major areas of focus within our system. And the first is that all-important role of long-term preservation, and that's our data management and stewardship area. So that supports the other 2 areas, both our science information services work, which helps people know, learn, and grow in their understanding of the data and the oceans, and our data access work, which helps people access the data and metadata about the data to help bring that data to life. The SOTO, which you'll be seeing today, touches all 3 of those areas, but primarily it's in the science information and in the data access areas. So as mentioned, there's various services and tools and protocols that we use to reach out to our global earth science community, including direct access protocols, subsetting services to help you focus on just the data that matches your region of interest, a comprehensive web portal that allows you to view ocean stories, read up on the various missions and initiatives, and learn all about the data sets and access our tools and services. And then finally, visualization. The visualization capabilities are where you can view and interact with the data. So SOTO, our topic for today, is our primary visualization toolkit. So you're all invited to explore PO.DAAC via our website, and as a reminder, you can always easily reach SOTO by the link at the bottom right of our main portal. And within SOTO, you can then explore, examine, and participate in the science of the ocean itself. We hope you find the toolkit exciting and useful. Now, here to give you a look at that SOTO toolkit, I'm going to turn it over to my colleague, Kathy, who will provide an overview of the hows and whys of SOTO's features and capabilities. So, Kathy?
Thank you, Eric. Hello, everyone. This is Kathy Toll, and I will be giving an overview of SOTO, its key capabilities, as well as the future near-term and long-term development plan. In the next presentation, Flynn, the SOTO front-end developer, will provide a demonstration of those capabilities within SOTO. What is SOTO? SOTO is a trusted, interactive, web-based visualization tool to communicate the state of the ocean. So, how does SOTO communicate ocean information? With oceans of data currently available, how do we know what data is best to choose that is helpful to accurately review the ocean information that we're looking for? With that question in mind, we developed SOTO. SOTO's key function is to transform science data into information and then visualize that information through its visualization toolkit. For experts in ocean information, SOTO then goes deeper in serving it as a tool to explore and detect ocean phenomena. We will see that later on in its presentation. With all that being said, behind SOTO are a group of oceanographers at PO.DAAC that come together to select which data to present and then define the visualization capabilities to bring out that ocean information and put it at your fingertips. So here we are as the SOTO team proudly sharing this tool with you today. So there are 2 main pieces to SOTO. The first piece is the datasets. The datasets are the building blocks which we use to build that ocean information. Each key ocean parameter as well as additional Earth system parameters have datasets selected that represent those parameters with a goal of 1, piecing a complete scientific picture of our oceans and climate, and second, to accurately serve as a tool to explore and detect ocean and climate phenomena. The second piece of SOTO is the visualization toolkit. So now I will briefly describe the interactive map capabilities that SOTO is currently offering. First, full historical records available to each of the datasets within SOTO. At the bottom left corner is the calendar widget. With full historical record available, the calendar allows stepping through the full historical record, and the animation capabilities allow time series animation with selectable speed and step size. The interactive color bar shows values with units on mouse over. Another key feature is the data preview option that allows a quick data comparison across active dataset layers. As you mouse over the map, you can see the latitude and longitude as well as the estimated value. Just like what I have there it shows the sea surface temperature measurements from those different datasets that are roughly within the same range. And finally, after playing with the tool and setting up the view that you want, then that view is capturable and shareable with others as a URL, letting them see exactly what you are seeing. As mentioned earlier, one of the two key pieces of SOTO is the datasets themselves. So I want to show what we're capturing in the flyout and documentation. Each dataset is provided a documentation page. It includes a brief description of the dataset, the rationale of why the dataset is chosen, the dataset time span, and the SOTO image latency, which is when we should expect a new image to arrive in SOTO. It also includes the data processing steps that show how we went from science data to the visualization image that we display in SOTO. As for future developments, there are near-term and long-term goals. The near-term goal, there are 3 additional datasets that will be available in the next major SOTO release, which is currently planned for this summer timeframe. Adding to that will be image and animation export. We also plan to provide charting and plotting capabilities, such as time average map, a Huff-Miller plot, and time series for a bounding box, along with basic statistics. For the longer-term future development plans, there are these are the areas that we want to mature SOTO over time. Of course, we will continue to expand our dataset listing to present a more and more complete scientific picture of our oceans and climate. And to the right, you can see there are already a list of datasets additions to be considered. One of the most requested features is to be able to do color bar rescaling, and that would change how we render our images. So currently we pre-render them, but to do rescaling, we need to be able to do dynamic rendering. So that's a big challenge, but dynamic rendering could open up a lot of good features like recoloring and reprojection as well. So we're looking forward to that. Finally, we'll be working on evolving the plotting and charting capabilities to move beyond bounding boxes and to work also with points and lines. So that's an overview of SOTO and its key features and plans. And next, my colleague Flynn, who is the SOTO front-end developer, will give you a demonstration of those capabilities, focusing on functionalities useful for science applications.
Thank you very much, Kathy. And yeah, so here we go. We'll take a look at a high level what this application can do. So here we have state of the oceans loaded by default, and you can see we have a large map in the center. We have dataset controls in the upper left. We have a timeline across the bottom. And this big map in the center is fully interactive. You can zoom, pan around, either using those buttons you see down in the bottom right, or with your mouse wheel and even some keyboard controls. You can also reset the view to all the way zoomed out. But let's dive right into the dataset controls there in the upper left. So you can see by default we have 4 layers available, or 4 datasets available, with sea surface temperature being active by default. And what we can do is we can use those toggles to turn on one or more of those datasets at any given time. You can see I've turned on ocean color, or chlorophyll, and then we can use
add more to explore the full range of data sets available within this application. So here we have the data sets broken down by their parameter on the left. We have the list of data sets matching that parameter in the middle. And then if you click on any of those data sets, you can read some of that information that Kathy was mentioning earlier on the right. So here I'll turn on ocean wind speed layers. And you can see I'm just selecting those with the checkboxes. And now when I go back to the map, you can see I now have those two data sets active and available in that list in the upper left. So here I'll zoom into an area just so we can get a little bit better visual distinction between those layers. And I'll go back to the data set menu and I'll start using the opacity control. So here as I move that slider up and or left and right, you can see that ocean color layer fade in and out on the map. And that can help you explore data sets alongside each other if you're looking for features that match between the two. Right next to that opacity control, we have layer ordering adjustment, where you can change the display order of these data sets on the map. So here I'm moving that same ocean color data set up and down in the display stack, and I can do that with any of the layers. So now I'll move that one of those ocean wind speed layers up and down. You can see it change in relation to those other two layers displayed on the map. Right next to those controls, we also have a color bar that, as Kathy was mentioning, is interactive. So I'll turn off those two wind speed layers, and now as I move my mouse across the ocean color bar, you can see an approximate value associated with that color as displayed on the map. Right next to that color bar, we also have a More button, which if you click on, you can see additional controls that are given to you for each of these data sets. So we have that same layer positioning adjustment, we have the same opacity adjustment, but now we also have color bar adjustment, where we can drag the two ends of that slider to mask off ranges of values for each data set. Now here I've masked off some of the lower values for that chlorophyll layer, and now I can use that squash palette button to now restrict the range of those colors to that new selected value range. Now this isn't true rescaling, this is an approximate rescaling to provide a little bit more contrast in the display. And I can also display that color bar on the map and close the menu, and now I have a trimmed down UI to be able to explore that data set on the map. Now I'll remove that color bar from the map and I'll reset the color bar for that layer. And then we can go back and look at some of the last control that we have for each data set, which is that layer info, again, that we saw when we were adding layers and that Kathy touched on in her presentation. If we click on that eye, we can read about the data set title, a little bit about that data set, why we included it, the time range for which we have data, additional resources provided by the DAAC, as well as a description of how we generated these images. So the next part that I'd like to show you is the time controls. And this is the time slider down across the bottom, as well as the current date indicator. So I'll turn on sea surface temperature anomaly for some more visual contrast. And now if we look in the bottom left, you can see I'm adjusting the date by using the toggle, the buttons above and below the current date display. So I can move by day, I can move by month, and I can also move by year by using those buttons. They're also inputs, so I can type right into them. And right next to that current date display, we have a shortcut to jump to today, but since this is a pre-rendered video, that's not entirely meaningful. Right next to that, we have a time slider where you can click on individual days. You can also grab the current date indicator and drag it across the timeline to do a quick scrubbing maneuver to see the data set change over time. But to do that more efficiently, you can also use the animation panel, which I'll open up now, and you can see we have the ability to select a start date and end date. We can also set the speed of the animation, which I'll set to fast, about 5 frames per second, and we can set the step size. Here I'll set it to days, and then I'll hit play. And you can see it start to buffer the data within that selected time range, and then once the buffer is loaded, it'll begin to play. Now that is a rolling buffer, so if you happen to see the loading come up in the middle of an animation, it's not broken, that's expected. Now what we can do while it's animating is we still have the ability to adjust things like layer ordering and opacity. So if you're animating more than one layer at a time, you can still explore them alongside each other. We can also adjust the playback speed of the animation while it's going. So here I'm setting it to fast, and now I'm setting it to slow, about 1 frame every 2 seconds. Now here I'll stop it again, and I'll demonstrate selecting the time step option. So I'll turn on sea surface temperature, and I'll set the playback speed to about medium. I'll extend the time range to about a year, December 1st to December 1st across 1 year. And then I'll set the time step to 1 month. Now this isn't performing interpolation, it's simply sampling every month along the selected time range. So once I hit play, you'll see this data set animated over a year, taking the first of each month. So I'll collapse the menu out just so you can see that a little bit better. And again, once you hit play, it'll start to buffer up the frames within this animation, and once it's done, it'll automatically start playing. So now we can start to see this data set, how it changes over much larger time scales. Now while you're playing an animation, it can be useful to use what we call the distraction-free mode, which I'll activate now, which hides most of the interface to give you a very minimal view of whatever data you have displayed on the map. Now the next section that I'll be looking at are the map tools, of which this distraction-free mode is one. So as mentioned before, you have the ability to zoom in and out of the map using keyboard or those controls down at the bottom. So here I'm going to zoom into just a feature on the map, nothing terribly special about it. It seems some anomalous cooling. And then I'll turn on measurement of area. And I did that by selecting measure area from those map controls. And now I'm drawing an area just by clicking around different points on the map to form a polygon, which when complete will give me a quick readout of that area. So it's approximately 7.6 thousand kilometers that I'm measuring. So I'll remove that measurement from the map, and now I'll turn on data preview. Now when I move my mouse across the map, you can see an approximate readout of the values where my cursor is. And you can see that cool area is somewhere around 20 to 21 degrees Celsius. And this works for multiple layers. Now I'll turn on that sea surface temperature anomaly layer, and I'll bring that opacity down so we can see the sort of structurally match up the those two data sets. And now as I move my mouse across the map, you can see not only the sea surface temperature, but also the anomalous temperature. So it's measuring somewhere between 20 and 21 degrees Celsius, which is anomalous by about -3 degrees Celsius. Now the last section that I'd like to look at with this application are the miscellaneous tools in that data set control area. So right above that we have help, which provides pages with about text, FAQs, system requirements, and when you click on them you can read about the application and some quick help about it. Right next to help we have the share modal, which when you open it you are given that URL, which as Kathy was mentioning can allow you to share this application state with your colleagues, as well as some social media shortcut buttons. Right next to that we have settings where you can adjust things like the base map, as well as the units with which measurements are displayed. You can also turn on layers like coastlines, borders, roads, and place labels to give yourself a bit more spatial reference, especially over land. And then if I turn on some layers, change the base map, things like that, and then zoom into an area, such as Los Angeles, where I happen to be, we can then open settings back up, and that last button down at the bottom, Reset Application, will return you to the default application state. And that about concludes everything that I wanted to show you with the applications. Now I'll turn it over to Ed Armstrong to give you a better idea of how a data engineer or researcher might use this application.
Well, thank you, Flynn, and welcome everybody. I'm Ed Armstrong, and I'm going to give you, we're actually going to do like a live drive now of SOTO and investigate a few interesting oceanographic use cases for, from the perspective of discovery and data exploration. So as both Cassie and Flynn mentioned, you can actually capture the state of a SOTO tool, namely the layers, the region of interest, and various other metrics. You can actually capture that in a URL, and that's what I've done here. It's just been pasted into a Firefox browser and executed. And what we're looking at here is a region off the Mexico coast there in the Pacific Ocean called the Gulf of Toolkit, where you often see very interesting changes in the oceanographic surface conditions due to the interplay of the wind field on the surface of the ocean. So what we have loaded up here is two layers. There's a set of vectors and arrows. Those depict the wind field as measured from a satellite sensor called ASCAT. It's actually a radar sensing instrument, and by measuring a radar backscatter from the ocean surface, you can actually derive the ocean surface wind speed and as well as its direction. So that's what we're seeing there is a collection of arrows. There's both daytime and nighttime observations as this satellite is orbiting the Earth, and of course it doesn't observe everywhere because it has a limited swath. Beneath that, we see a sea surface temperature layer that's derived from this product called MUIR, which is a daily global level 4 gapless gridded sea surface temperature field that's essentially merging sea surface temperature observations from a large collection of both infrared and microwave data sets. And we're not looking at the absolute SST, but what's making this area interesting is we're actually looking at the anomaly SST. So we've subtracted a long-term climatology from the absolute SST value. And we see these very anomalous cool signatures here in the Gulf of Tonopec on the order of about 3 degrees. And of course, overlaid there is the wind field. And you can also look at the magnitude of the wind speed by associating the color of the vector. So I'm pointing to one vector here in kind of the middle of the cold core eddy right here, and it's kind of a light green. So we can come over here to the color scale, and you know, that's on the order of about 15 meters per second. So, you know, those winds are in the range for about 10 to 20 meters per second, you know, blowing on the order of about 20 to 40 knots. So that's a pretty significant wind field. So what's going on here with regards to the physics? Well, the wind field, these winds that are blowing here in the Gulf of Mexico, they actually get to the Pacific by going through a narrow lower topography gap here between two moderate mountain ranges. And they essentially get compressed and they accelerate, and then they can blow over here. Once they get to the Pacific side, they intensify and blow right over the ocean. Of course, as you might imagine, or you know anything about oceanography, these strong winds will cause a surface divergence in the upper ocean, and essentially we'll get upper ocean upwelling, where a strong divergence will advect the warmer water to the right of the wind field, and then cooler water will come beneath it to replace it. Often this cooler water also is very high in nutrients, and we'll see some effects of that as well as we kind of work through this little use case. So this is an event. These events often occur in this area because of these very strong winds. It's actually an area of hurricane initiation, and because of these very strong clearing winds, I'm going to turn on the true color field right now just to show you that this area is often very clear. There's because of these strong winds, there's a lot of cloud clearing, so it's a very good area to do some satellite oceanography in the optical and the IR bands. So this is an event last year. I have it on the, you can see the little calendar there to the left-hand side. This is November 15th of 2017. And we can kind of step through this particular event here and see how this feature kind of waxes and wanes. So if we maybe step to the beginning of it, and we'll go back to November 10th, and you can see in this case the wind field was still strong, but there was really not too much cooling going on yet. You see a small evidence of some cooling already starting to happen in this area right here with very blue and green colors right there indicating that it's cooler than normal. And of course, the reds indicate that it's warmer than the longer term average. And so if we can step forward, you can see at how this cool core feature here starts to wax and wane. So as we march on here, now we're at the 11th, it starts to build. You know, the wind field is still very strong, very highly, spatially the cool SST is highly correlated to the strong winds. Now we're back to the 15th where it's really intensified. And then it starts to move around a little bit, advect to the west, and then it gets the dimensions even further by the time we reach November 20th. So one of the things that you can do, I mentioned earlier as well, is that you can adjust the colors of some of these layers. And you know, sometimes when you're overlaying various layers on top of different fields, some of the colors might get obscured a little bit. So in this case, you know, some of these winds, you might kind of like lose the distinction of the winds that's kind of crossing here in this area right here where we have both green SST and a green wind field. So what we can do is we can come over here and adjust the color of the wind field for this particular layer and let's say set it to black, right? And so now we can see the actual direction much more clear. Of course, we've lost the definition or the delineation of the magnitude, right, because everything's just black, so there's no colors that you can actually associate with a color bar over here. But that's all in well. We can also turn on the data preview here to actually get some absolute SST values as we kind of scroll around here. As I mentioned, these are all on the order of about 3 degrees Celsius right here. And then, of course, it gets a little less warmer here. And to the left-hand side, to the west, there's actually a warm core eddy right there where it's actually warmer, 1.7 degrees warmer than the long-term average. Now, as you might imagine, one of the correlations you might be interested in looking at is what is the correlation between these types of event and the ocean productivity as measured by chlorophyll A from a satellite sensor. So, we have an upwelling event here, and as I mentioned, upwelling often draws cooler, nutrient-rich waters to the surface, and so we might be, naturally expect that there might be a chlorophyll bloom associated with these types of events. So let's step back to the beginning of the event around November 10th right here, and we'll come back over here, and we'll turn on a chlorophyll layer right here. And so this is the ocean chlorophyll as measured from the aqua sensor. And of course, the reds and the orange indicate areas where you have very high biological productivity. The green is moderate productivity, and of course, the blue is more open ocean. We call it the oligotrophic, where there's not much productivity going on. And so I can adjust the opacity of this chlorophyll layer so we can kind of peek and see both the chlorophyll and the cool SST and to see perhaps how they interplay amongst each other. So I can kind of back this opacity of this particular chlorophyll layer a little bit off, and maybe just so that we can see the underlying temperature signal. Okay, so there's temperature right there, and you can see the little initiation of a cooler temperature right there. So I'm going to maybe set the opacity to maybe kind of right there, about 60%, see how that looks. I'm going to step through our little time series here. Let's watch how the chlorophyll changes and is associated with the cool core eddy. So that's the 10th, and now we're stepping a day ahead. I'm stepping one day at a time. You can see the cool core eddy started to take off. There's still very high chlorophyll just right at the coast. But as we kind of step through, we can see that the chlorophyll, as the cool core eddy starts to wane a little bit, the chlorophyll is really taking off. And so it's kind of what we expect. There's a delayed mode of perhaps a few days lag of a chlorophyll bloom to the advent of nutrients that came to the surface due to this upwelling event. And so this is really kind of a little bit about what we might expect. They're not quite spatially correlated. Of course, there's a little bit of temporal lag as well, but we're definitely seeing some correlative activity of biological productivity to this recently upwelled water. Now the cool core eddy is starting to wane a little bit. We're at the 20th, but this actually, this play of the wind and the response of the ocean surface really, kind of modulates in this area during this time period on a biweekly time frame. And so actually it kind of kicks off again if we watch both the biological productivity and also the cool core eddy. It really now, you can see a very large cool core eddy, very high productivity, very tightly coupled with that cool core right there. Very, very interesting qualitative correlative relationship there. And so it's actually peaking now again and moving around in different areas. So that's one way a researcher could use this tool to do some cursory investigations of oceanographic phenomena in this area, and of course play around with the different layers. We have the wind field, of course, the chlorophyll, the SST, but there are other layers there, including ocean surface currents and salinity as well. So I'll move on to another use case now, and in this case we're going to be looking at more of a basin scale type feature, and this is going to be the evolution of the last El Nino, and we're going to be looking at a snapshot of a time series of 2015 to about mid-2016. And again, I have overlaid the Muir SST layer, and this is now the absolute SST. It's not the anomaly yet. But what I wanted to show you is that if we zoom up into this area here, that's the Eastern Pacific, where the dominant El Nino signal is apparent. And as I mentioned, I forgot to mention, I've had this animation now preloaded up, and it's actually at a monthly time step. So even though this layer is at daily, I can actually step through the time series on a monthly time step. And that's what I've done just to, because there's just like an overwhelming number of time steps in the time range that I've chosen right here. And so what I wanted to show you here is that as we step through this time series here at a month, unless you really have an expert eye and really know kind of what the oceanography in this area, of course there's these characteristic tropical instability waves here, these wavy features, and the equatorial cool tongue. But unless you're really an expert in this area and you're looking at the absolute time field, as you're stepping through the thing and getting closer to the El Nino, unless you're really an expert, you don't really have the strong evidence that an El Nino is rapidly intensifying and underway. So now we're September, we're kind of approaching the peak El Nino period. You're still seeing these evidence of these tropical instability waves. It might be a little bit warmer to the untrained eye, but you don't, unless you have a really trained eye, and you might not get the feel that a strong El Nino was underway. So what you really want to do is look at the anomaly layer, right? Again, that's the long-term, the time series, the mirror time series, where a long-term climatological reference field has been subtracted. And so if you look at the anomaly time series, of course, things jump out at you right away. And so if we go back here to the beginning and play this animation, you really kind of see the evolution quite obviously of this last really big El Nino that occurred in the winter of 2015-2016. So it takes a while to buffer and load up, and now it's running. It's stepping through the monthly time steps. You can see the little calendar on the left-hand side here. We're already up to July of 2015. And you can see this area, this El Nino is rapidly intensifying and now has peaked towards the end of 2015 and then decreases as we step into mid-2016. So I'll let that play one more time. So the key kind of message I wanted to show you here was that, in this case, you really wanted to target the anomaly SST layer to be able to look at this type of phenomena. If you just use the absolute, you really wouldn't get the feel or the sense of the scale and of the scale of this particular large El Nino feature. There's certainly other layers you could look at here. For instance, you could turn on the the surface currents. We call them the Oscar surface currents. They're also derived from satellite measurements of both temperature and sea surface height. We get global ocean currents on about a five-day temporal scale. And so there's various things you can look at here with regards to, possibly how the currents might be changing in response to El Nino as well. So I think I've run through those two use cases, and I'm going to go back to the Gulf of Tehuantepec use case in this area right here. And, one of the questions that often get asked is, this is a very nice tool, but how do I actually get access to the various layers that I'm looking at here, right? So I might want to access either the wind field or the temperature that I'm looking at here. And so how do I get access to those particular information? So unfortunately, there's no direct way to get access as of yet. As was pointed out by Flynn and Kathy, there are the pointers to the data set information pages for each particular layer that you have loaded up that give you metadata and the endpoints with regards to accessing the granules. For instance, it'll give you the PO.DAAC locations or perhaps particular tools like high tide that can be used to extract the data. But the user really kind of has to know the time and space dimensions of the particular layer they're looking at, and then use a tool to go make a request to access the data and extract the data if they say want to use it in further analysis programs like a MATLAB or IDL or Python. So in this case, let's say I wanted to extract the absolute value of the SST right here, not the anomaly, but if I wanted to look at the mirror SST right here in this region here, I would have to know something about both the time and the space part of the subset request. So, the time part, as I mentioned, we're looking at about the 10th of November to the 20th of November of 2017. And the space part, you can kind of eyeball here. There's actually a lat long box right here as I'm moving my cursor around here to give you some idea about, actually the exact location in the image that I'm looking at here. So in this case, I want to make a subset request from about 20 north to 10 north and about maybe 100 west to maybe 90 west to kind of capture this little area here, maybe a little bit bigger to capture this little area here where these Gulf of Tehuantepec upwelling features are evident. So I have that information. I can use various tools to extract a gridded layer such as this. This is actually a gridded product. If I wanted to extract the ASCAT, I would have to probably use a different tool, a level 2 subsetter called high tide. And we actually had a webinar a little while ago about that. And so if you wanted to go back to learn about high tide, you could go back in the archives and review that. But in this case, it's a gridded product. And so Typically, we use things like PO.DAAC and threads, which are both web services for extracting out gridded products where you simply access a thread server with a URL and it will spit back aggregated data. So that's what we're going to do right now. We have a thread server running at the PO.DAAC, and in conjunction with a thread server, they have what is known as a NetCDF download form, and this is essentially an interactive form where the user can essentially select a product and various subset boxes that they can use for their extraction, as well as the time range. So they have to have some idea of the time range and both the space dimension. And then once that information is inputted, the tool will spit back simply a URL, and you can use that URL either directly to cut and paste it directly in a browser, or to call it in a script, in a Python or a MATLAB script, to actually extract and subset the data. So this tool actually does both subsetting of the data, and it actually does the aggregation of the data. And what you get back typically is a NetCDF file. So I've done this for the Muir SST. I've constructed a URL that has the proper space-time dimensions inside the URL, and I'm going to execute it right now. And so this is the URL you see right there where I've put in all the different coordinates. And so I'm just going to execute this, and it's going to take a few moments as the web service makes the request to the service, to the thread service, and then does the data extraction and as well as the packaging, and outputs a NetCDF file. So it's done that now, and I've actually associated NetCDF in my particular computer with a application called Panoply, which is a nice NASA-developed tool for doing data visualizations of NetCDF and HDF files. And so it's automatically been associated with this file that this thread server spit out. So I'm just going to open it up in Panoply, and we're just going to kind of look around a little bit of some of the variable that got outputted. In this case, we did the analyze SST. So let's just kind of plot it up. This is actually data now, so it's data that's been packaged in a NetCDF file, but we're just going to do some simple plots right now. Oops, let's try to reopen it again. Okay, there it goes. Okay, so let me see where that file got downloaded to. Downloads. Okay, there it is. So that's the file that just got spit out by the Threads NetCDF server, and we want to visualize the analyze SST variable. We'll just double click on there. And so there we see a plot, and of course it's nice cookie cut out there in this region of interest right here. And I'm just going to kind of zoom up there. And so there's, of course, of our cool core eddy there in the Gulf of Tehuantepec off Mexico. It's maybe a little bit bigger than it needed it to be. But this is what I mentioned, for that particular 10-day time series, all those 10-day time steps have been packaged into a single NetCDF file. So we can step through this thing, and we're stepping day by day now. Now we're at the November 12th there. And you can see how this eddy, cool core eddy, grew and then de-intensified somewhat. Now we're at the 20th. So in a nutshell, I've shown you here how you can easily extract some of the gridded layers that the user can use in SOTO, as well as working through a few different use cases of oceanographic phenomena discovery using SOTO. So that comes to the end of our interactive portion of our presentation, and I'm going to turn it over back to our host, Jennifer, and we can hopefully engage you with some questions if you have some. So thank you very much.
Okay, wonderful. Thank you, Ed. So at this particular point, what we will do is we're going to transition to the end polling questions. These are also optional. We'll give these probably 3 to 4 minutes or so, given the fact that many of them are short answer questions. And then from there, we'll move directly to the Q&A period. So if you asked a question earlier and you don't see it right now, not to worry. That's a persistent feature within Adobe Connect, and we'll see your questions in just a few minutes here. So let's give these about 3 to 4 minutes, and then we will address questions during the Q&A period. All right. This is really excellent feedback, everybody. Thank you for taking the time to answer these questions. We're going to give this another minute and a half or so, and then from there we'll jump to the Q&A. So be sure to stay in the virtual meeting space or online to participate in the Q&A. All right, thanks everybody. Okay, everybody, with that, we are going to transition to the Q&A period. If you think of something as we're going through this, feel free to jot it down in the Q&A. And I received a question earlier on here, so I'm going to go ahead and pull that question up here. Give me 1 second. Okay, the first question was, are you considering using existing web services like NCWMS or rolling out your own?
So in terms of visualization, most of the visualizations that we're doing right now falls into one of two internal tools that we have and goes through a workflow in our back end. There's a lot of options that we're looking at and trying to ramp up the performance of that, and all in an effort to get us more towards that dynamic rendering. So yeah, lots of different services are on the table right now. It's a good question, and we'll be taking a look at all of those over the next several months, trying to see what's the best option to maximize the efficiency of doing that visualization. A good question.
Okay, thank you, Eric. So the next question, and if I don't have this right, if the user could add additional detail, at a certain point, Ed, you had mentioned one of the users wanted you to share the links for the data granules import system to SOTO, and I'm not sure the data. Do I have this correct for the participant who had the question? In the meanwhile, while we're waiting here,
I could do my best to answer what maybe I think he was asking for. So essentially in my demonstration, I showed how one would use two different types of URLs. For one, there was the SOTO URL where we actually captured like a state. In this case, it was the Gulf of Oceanography or the El Nino, where I captured the number of layers, or if I wanted to do an animation, the zoom level of the region. And then the second part of the demo, where I did a little bit of the data extraction, I was showing how essentially you can use a web service like Threads and just call it with a URL, where you're simply passing in, say, a parameter and a space-time box, and then getting back aggregated data, subsetted data at the end of that web service request to a Threads data server.
Okay. Okay, great. So that answers the question. So the next question that we've got here is, can you share the list of data sets that are currently available in SOTO? I missed the list earlier.
So the full list of data sets, we don't have that captured as an image in the presentations, but it's easy to get them. If you go into the SOTO tool itself, there is a button in the upper left area of the screen to add more, and as you scroll through that, then you'll see the full listing available. There's a count by category or by parameter type, and then there's also in the middle of that window that'll pop up, there's just the full list end to end of all the data sets that are available. So that's easiest actually to view just by going to the tool itself and clicking on the Add More button.
Okay, great. Thank you very much. And then if you could share the Threads data server URL, do you happen to know that off the top of your head? If not, it's certainly something we can follow up with, the participant offline as well.
Yeah, I can grab that set of URLs and paste it in the chat box, I think. Can I do that?
That would be great. That would be great.
Okay, I'll do that right now.
That sounds wonderful. Okay, are there additional questions? While we're waiting to see if there are additional questions, okay, great. The next question actually has to do with whether or not we offer any kind of certificates for the webinars. These are not, how should I say it, like part of a series where they're considered continuing education, if you will. I don't know if that makes sense. And so I guess the best certificate, we don't offer an official, webinar completion certificate. The proof that you had attended the webinar would essentially be, perhaps your webinar approval message, that kind of thing. And feel free to email me offline if you'd like to discuss further. So right now what I'm going to do is copy the Threads link into the pod for everybody. And hold on one second. There's a second. Basically the landing page, if you will. Hopefully our participants can see that. And just a couple of things. We do have an additional question. However, in the meanwhile, we've included the specific use case example. There's a tiny URL, a bit.ly shortened URL for that particular example. Will take you right into SOTO, the state of the ocean. There's the link to the application as well as the link to the PO.DAAC. And then below, in the lower right-hand corner, you will see the presentations for today, with the exception of the video, which was too large to place into the share pod. And so the next question is, are there any plans to add SMAP salinity?
Yes, actually, the SMAP salinity layer should be coming through in the next version of SOTO. And that will be roughly summer of this year.
Okay, thank you. And let's see, the next question is, can we plot any kind of point data in .mat format, for example, extremes, etc.?
So for the .mat question, it depends. If you're talking about Panoply, or are you talking about SOTO? In SOTO, we generate our own images through what Gibbs, as Eric was speaking about before. So they're actually KML files. If you have your own .mat file, there's no way currently to import that into SOTO. And then for Panoply, I believe Panoply only reads NetCDF and HDF files.
Okay, thank you, Jessica. And let me just pull up the questions here again. Okay, and is the SOTO application freely available? Yes, it is. That was this particular participant was having some issues with his audio a bit earlier on. And so, Edward, you also have a web link to that directly below in the web link share pod. Are there any additional questions? Okay, there were some additional links that Ed Armstrong had placed in the presenter chat. The one has to do with subsetting. I'm going to go ahead and paste these in here for all of you, for those who may be interested. And I should tell you that you'll see the Q&A pod. You'll see these if you listen to the recording at a later date. But certainly feel free to contact me if you'd like to get in touch with any of our speakers offline at the PO.DAAC. Okay. Any additional questions? Let's see here. Just checking out to see if there are any additional questions. If there are no additional questions at this time, what we'll do is we'll log off from the audio component of the webinar, and I will leave the virtual meeting space open an additional 10 minutes for those of you who may think of a question that you'd like to ask or are interested in downloading today's presentation files. And then just as a quick reminder, I will also email the recording links out to not only the participants, but everyone who registered for the webinar. So if you have a colleague who registered but was unable to attend, not to worry, they'll be able to listen to this particular webinar at their own leisure at a different time. Okay. I don't see any additional questions at the moment. Thanks to all of you for participating today. We really appreciate it. Our next webinar will be held at the end of February, and we'll focus on data products and tools at our Atmospheric Science Data Center. So stay tuned to the tinyurl.com Earth Data webinar for information in the upcoming week or so. All right, thanks everybody. At this point, we'll log off from the audio component. Thanks to all of our speakers, and we'll leave the virtual meeting space open. All right, thanks so much. Bye-bye, everybody.